Out in the distant reaches of the solar system, everything should be silent and frozen. But in one place, the surface is constantly breaking apart. Lava is blasted into space, and a massive planet dominating the sky relentlessly stretches and twists this world. Io, the result is non-stop geological activity. So how does this small moon become the most active world in the solar system? How can something so small be this violent? In 1610, Galileo Galilei made an observation that would change humanity's understanding of the cosmos. While studying Jupiter, he noticed several points of light moving alongside the planet. At first, they appeared to be ordinary stars. But over time, it became clear that their positions were shifting, and that they were orbiting Jupiter. This discovery marked a major turning point, challenging the long-held belief in an Earth-centered universe. These four objects would later be named the Galilean moons: Ganymede, Europa, Callisto, and Io. The other three moons would eventually be known for their cold, frozen nature. But Io turned out to be completely different. For a long time, Io remained nothing more than a small point of light. Its surface could not be resolved in detail. But when modern spacecraft reached the Jupiter system, everything changed. It became clear that Io's surface is not stable. It is constantly being reshaped. This discovery transformed Io into one of the most active and unusual geological worlds in the entire solar system. There isn't a single factor behind Io's extreme activity. The key lies in its location. Jupiter exerts an enormous gravitational pull on Io. But this alone is not enough. At the same time, Europa and Ganymede also apply their own gravitational forces. This three-body interaction prevents Io's orbit from being perfectly circular, making it slightly elliptical. As a result, Io is sometimes closer to Jupiter and sometimes farther away. This variation leads to a critical outcome. Io is constantly being stretched and compressed. This does not happen only at the surface. The entire moon deforms, including its interior. Calculations show that these tidal forces can raise and lower parts of the surface by tens of meters. For solid rock, this represents an extraordinary level of deformation. This continuous flexing generates intense friction within Io's interior, and that friction produces vast amounts of heat. The resulting internal heat creates large regions of magma beneath the surface. When this magma reaches weak points in the crust, eruptions occur. That is why volcanism on Io differs from what we see on Earth. It is not driven by plate tectonics, but directly by tidal heating. Consequently, Io becomes the most volcanically active body in the solar system. When Io is viewed from a distance, the first striking feature is its unusually colorful surface. Yellow, red, orange, and even greenish tones appear across the landscape, completely breaking the expectation of a simple rocky world. The main reason for this appearance is that the surface is not dominated by silicate rock alone, but largely by sulfur and sulfur compounds. Io's volcanoes do not only eject lava, they also release large amounts of sulfur and sulfur dioxide gas into space. These gases rise, cool down, and eventually fall back to the surface. This process behaves almost like a continuous form of rain. As a result of this, the surface becomes divided into colors depending on temperature and chemical conditions. Yellow regions indicate solidified elemental sulfur. White and bright areas represent frozen sulfur dioxide deposits. Red and dark regions mark zones that have been altered by high temperatures and active volcanic processes. For this reason, Io's surface is not static. It is constantly changing, resurfacing, and erasing its own past. This dynamic nature leads to another important consequence. Impact craters are almost absent on Io. Any crater formed by incoming meteoroids is quickly buried by lava flows or resurfacing events. What this means is, Io's surface continuously resets itself. This active behavior also leads to the formation of massive lava lakes. One of the most notable examples is Loki Patera. It is approximately 200 kilometers in diameter and represents a vast, constantly changing magma region, where the surface repeatedly forms and collapses. But there is a crucial difference here. Volcanoes on Io do not usually build conical mountains like those on Earth. Instead, the surface collapses, and wide, flat lava fields are formed. What this means is that Io's landscape is shaped less by rising volcanoes, and more by collapsing terrain and spreading lava flows. The overall picture is clear. Io's surface behaves less like a solid crust, and more like a constantly rewritten system. When looking at Io's surface, an apparent contradiction emerges at first glance. While everything seems to be constantly melting and flowing, some structures rise to extraordinary heights. These are especially the isolated, sharply pointed peaks. One of them is known as Steeple Mountain. Such features can reach heights of 5 to 7 kilometers. Some even rise up to 15 to 18 kilometers, making them taller than Mount Everest. But there is a crucial difference here. These mountains do not form ranges. They are not connected in chains. Instead, they rise in complete isolation. This indicates that their formation mechanism is fundamentally different from that on Earth. Io has no classical plate tectonics. What this means is that mountains here are not formed by continental collisions. Instead, a different process takes place. As magma moves beneath the surface, it creates voids in certain regions. Over time, these voids cause parts of the surface to collapse. At the same time, surrounding regions are forced upward. So while the surface sinks in one area, the crust is pushed upward elsewhere. This compression produces large, suddenly uplifted blocks of rock. These blocks then evolve into steep-sided, sharply peaked mountains. For this reason, mountains on Io do not grow gradually, are not shaped by long-term erosion, are not formed by tectonic plates. Instead, they emerge through sudden, large-scale crustal movements. This makes them some of the most unusual geological structures in the solar system. The resulting landscape is unfamiliar. Rather than continuous mountain ranges, there are isolated stone towers rising alone from collapsed terrain. Io does have an atmosphere around it, but not in the way we normally understand one. A dense, thick, and protective layer of gas would be expected. But on Io, the situation is the complete opposite. The atmosphere is extremely thin. In some regions, it is almost negligible. However, it is not entirely insignificant. Most of this atmosphere is made up of sulfur dioxide gas, and its source is directly the volcanoes on the surface. As volcanoes erupt, gas is released into space. A portion of it forms a temporary atmosphere around Io. It then quickly cools and falls back to the surface. What this means is that Io's atmosphere is not stable. It is constantly forming and disappearing again. There is another interesting aspect to this process. A strong difference exists between Io's day and night sides. In sunlit regions, sulfur dioxide vaporizes and the atmosphere becomes slightly denser. But as these regions rotate into darkness, temperatures drop rapidly. The gases freeze and settle back onto the surface. As a result, Io's atmosphere at night almost completely disappears. But the story does not end there. Jupiter's powerful magnetic field constantly bombards Io with high-energy particles. These particles interact with the thin atmosphere, and an unexpected phenomenon appears. Glows similar to auroras form around Io. But unlike Earth's auroras, these emissions are not concentrated near the poles. Instead, they often appear closer to the equatorial regions. At first glance, Io's surface appears extremely energetic, with constant heat, chemical diversity, and ongoing volcanic activity. Then a natural question arises. Could life exist here? As the details become clearer, the answer shifts quickly. The most critical missing factor is liquid water. Io is one of the driest bodies in the solar system, with no evidence of stable water reservoirs on or beneath its surface. The second issue is extreme temperature variation. Volcanic regions exceed 1000 degrees Celsius, while other areas drop to around -130 degrees Celsius. Such conditions make stable chemistry extremely difficult. The third factor is Jupiter's magnetic field, which continuously bombards Io with intense radiation. Under these conditions, complex molecules struggle to survive for long periods. For this reason, Io is not suitable for life in the classical sense. However, one detail remains worth noting. On Earth, microorganisms survive in hydrothermal vents without sunlight, relying on chemical energy. In theory, this leaves a very small possibility that simple life could exist in Io's subsurface, where heat and chemical activity are present. But current data suggests this is highly unlikely. The conclusion is clear: Io is an energetic and dynamic world, but its energy works against life rather than supporting it. Io is not a typical moon. Its surface is constantly reshaped, making it the most volcanically active body in the solar system. Juno has recently shown this activity in greater detail, while newer missions focus on more habitable moons like Europa and Ganymede, leaving Io in the background for now. Still, Io is unique. It is the clearest case of extreme tidal heating. Without understanding it, our picture of active worlds remains incomplete. Eventually, attention will return, because extreme worlds often hold the deepest answers. If you enjoyed this journey into one of the most extreme worlds in the solar system, consider liking the video and subscribing for more deep space explorations like this. It helps the channel grow and brings more content like this to you.